So let's go back to our main topic. What is a QR factorization? Let's remind ourselves. A QR factorization is an equation of the form A equals Q times R, where A is any m by n matrix with rank equal to little r. Q is an m by r matrix with orthonormal columns, and as we've seen, having orthonormal columns is the same thing as saying that the gramian of that matrix equals the identity matrix. And then R in this equation is an R by N upper triangular matrix. So for example, here's a perfectly good 4 by 3 matrix A, and I managed to somehow factor this matrix as Q times R here. So first of all, notice that R here is an upper triangular matrix. And then evidently, since I'm saying that this is a QR factorization, the columns of this matrix Q are orthonormal. And the way we would verify this for ourselves is we would take Q transpose and multiply by Q and check that we get the identity matrix. I also want to make sure that we're all paying attention to the way that the sizes of these matrices work. In a QR factorization, A can have any size, but then the number of columns of Q, which has to be the same as the number of rows of R, is equal to the rank of A. So because Q here has 3 columns, what we're saying is that A has rank 3 here. So it's important to pay attention to the way the sizes work here. Now, why in the world do we care about QR factorizations? Well, I hope to argue to you now that if we know that A is equal to Q times R, we can take a lot of the problems that we've been studying and simplify them. And a lot of the reason we can do this comes down to this theorem. Let's say that we have a QR factorization of a matrix A. Let's then look at the gramian of A. That's A transpose times A. Well, now we can substitute in Q times R for A in that equation. So now we're looking at Q times R quantity transpose multiplied by quantity Q times R. And remember that transposition is order reversing. So I can distribute the transpose sign here to obtain R transpose times Q transpose, and then I'm still multiplying by Q times R on the right here. And of course, the magic happens now. Now I see that in the middle of this calculation is Q transpose times Q, which has to be the identity matrix, because in a QR factorization, Q has orthonormal columns. So now that middle part of my calculation collapses to the identity, and what I'm left with is R transpose times R. So this calculation is telling me that in a QR factorization, A and R have to have the same gramian. So I like to call that the common gramian property. So when A equals Q times R, the gramian of A is the same as the gramian of R. And I want everyone to remember that the rank of the gramian of a matrix is always the same as the rank of the original matrix. So this also implies that the rank of A is always the rank of R. And then another consequence of this says that R is non-singular exactly when A has full column rank. If you remember the size of R in a QR factorization, the matrix R has the same number of rows that A has, that is equal to the rank of A. And if the rank of A is the number of columns of A, well, remember the number of columns of A is the same thing as the number of columns of R too. So having full column rank is the same thing as requiring R, the matrix in the QR factorization, to be square with full rank, which is exactly the concept of being non-singular. So how does this help? Well, another consequence of a QR factorization is that when A is Q times R, the columns of Q always form an orthonormal basis of the column space of A. So if you're studying A equals QR and you want a basis of the column space of A, you could just rip out the columns of Q, and that gives you an orthonormal basis of the column space of A. And one corollary now is that if A is equal to QR, the column space of A is equal to the column space of Q.